Okay, greeting to everyone who is watching this video. I'm Rui LI, and I'm going to present our works on test-driven software development platform for fog computing system. This presentation will begin with the background of the research, and then the overall framework will be presented subsequently. The preliminary works in the three directions will be explained in detail. Finally, a brief summary for you. With the rapid development of Internet of Things and 5G, we are now living in a world of smart services such as smart transportation, smart manufacturing, smart logistics, and smart health. So we all realize that AI and IoT means from Internet of Everything to intelligent connectivity of everything. Currently, smart systems are often developed and deployed in the mainstream cloud computing environment. Centralized cloud servers need to process a large amount of data through the internet by IoT devices, which bring critical issues such as high latency, high energy consumption, and data security. In recent years, fog computing, which is also called edge computing, is becoming the new generation of distributed computing paradigm due to its low latency and high flexibility by providing computing resource close to the end devices. However, as fog computing systems are normally complex in functionality, heterogeneous in computing resource, and distributed in system architecture, the development of fog computing system is a big challenge. Take Apollo platform as an example. Autonomous vehicle system requires toolkits to design, develop, test, and deploy software components for sensor collection, sensor fusion, perception, planning, and all these components need to be thoroughly tested in both simulated and real-world environment throughout the whole software development life cycle. This is our overall design for test-driven software development for fog computing system, named TDD for fog. This framework consists of three major parts. The left side of this framework is widely accepted three-layer fog computing architecture, which consists of end devices layer, edge node layer, and cloud server layer. For instance, in autonomous vehicle application, the end devices are those vehicle and edge node are roadside unit. We also propose a high-fidelity emulator for the underlying fog computing environment, which is shown in the middle of this framework. The emulator can reflect not only the network configuration, but also the physical attributes of each key component for the underlying fog computing environment. For instance, in autonomous vehicle, the emulator shall be able to provide highly accurate emulation for the vehicle network, along with physical emulation for each vehicle. To achieve extensibility of the emulator has an interface which allows to add or remove emulation components for specific fog computing system. On the right of this framework, we illustrate the TDD-based software engineering development lifecycle. For the development of microservice-based fog computing system, from a bottom-up design perspective, specifically, the typical test-driven utilities include metamorphic testing, mutation testing, and random testing, as discussed in background. Due to the lack of lifecycle support in major fog computing development platform, we propose to create software development lifecycle tools and matrix specifically for edge node and devices. The next step is to complete the development of TDD for fog. According to these three parts of the whole framework, there are three major research directions that we aim to investigate in the future based on the TDD for fog. In order to complete the development of mobile edge computing platform, we proposed a mobile edge computing and blockchain-based UAV delivery system to resolve the last mile problem in logistics. Specifically, this system is a typical distributed system with a three-layer architecture. A smart contract deployed on the blockchain are responsible for authenticating multiple UAVs and monitoring the UAV delivery process. A three-layer architecture is designed to provide real-time service for UAVs and provision computing and storage resources for the blockchain network. Specifically, it consists of cloud server layer, the edge server layer, and the end devices layer from top to bottom. We also proposed an energy-aware decision-making strategy for the dynamic task migration named GAD to optimize the UAV energy consumption. In addition, to take full advantage of MEC, an effective collaboration between the end devices and the edge server is essential. So we proposed Edge Forces, a devices edge collaborative framework for mobile edge computing-based smart system. In this framework, the original data can be pre-processed by the end devices, which will reduce the network traffic and also reduce the computation load of the edge server. In the direction of emulator, before this article was published, a preliminary simulation tool has been created to evaluate the runtime performance of four computing system named Workflow. Based on such toolkit, we now developed an edge computing-based workflow execution engine for smart system named Edge Workflow Rail. For now, Edge Workflow Rail is perfectly playing the role of the emulator in the TDD for fork. If anyone is interested in them, the links are provided for everyone to access them. For the test-driven development side, we preliminarily design and evaluate BMT, a declarative behavior-driven development-based metamorphic testing framework. It automatically translates a human writing behavior to a corresponding metamorphic relation, and synthesizes meaningful testing inputs using a variety of image and graphic processing techniques. Overall, we have made a great progress on all three research directions of TDD for fork, and the next step is to combine them to complete the whole framework. Thanks for your time.